the end of last week, just to remind you what we were doing, we had spent the last few lectures working on implementing a regular perturbation method to approximate the solution to, we started with a polynomial equation. We started with an equation that you can solve analytically. And we determined how we could approximate that and then compared those approximations to the exact analytical solution. Then we moved on to the perturbing an initial value problem. In this case, we looked at the projectile problem and looked at kind of how we're able to approximate that as our small parameter, which we had an idea of its physical meaning. We approximated that equation, the solution of that equation, to, I think, order epsilon squared. And then we moved on, just really to kind of show what is, how kind of broadly applicable these concepts are. We moved on to a system of equations, a system of differential equations that describe thermokinetics. And really, in a lot of ways, there's nothing new about that. It was more about kind of getting comfortable implementing these approaches. And in that case, we had more equations to deal with. They were coupled, so we had to solve them simultaneously. We now move on to a harder variant of the perturbation problem. And these are what are termed singular perturbations. So before I jump into singular perturbations, what questions do you have for me about regular perturbation methods, anything that we've kind of covered so far? Either your silence is complete understanding or complete confusion. I'm not really sure. I guess it could also be lack of coffee.
Ali.
Oops,
Hello, can you hear me?
Oh yeah, I have you now. Yep.
Yeah, I think, at least for me, I think just when we start doing the P set, that's when I'll realize what questions I have that haven't been answered. Once I actually get to try something entirely new on my own.
Okay, that's fair enough. Yeah, I probably should have split the problem sets up into two, because I know it's a long time before you start to work on them. So maybe I'll try to do that instead of what I was initially intending to do. Maybe I can do that after today's lecture. So that's a fair remark. The good news is if there are confusions about the regular perturbation approach, it doesn't go away. We still use it for these singular problems. So maybe what I'll do is I will kind of start working on one now, and it'll allow us to kind of see if any questions come up as we are introduced to this different approach. So I'm going to be going through a Mathematica notebook today, and if you want, then share my screen. Sure. Okay. So if you want, then you can go to the website bu.edu/mos/courses, and if you scroll down, I uploaded the Mathematica notebook I'm going to use today. It's under lecture 12. There's no video link yet, obviously. It's just a placeholder, but this is live, and so you can download this notebook if you want to follow along. But I'll be walking through the notebook as I always do, so if you want to kind of type and go, so you can get a feel for what we're doing and make your own mistakes, then I encourage you to do that. You can always kind of have this one open side by side. So while you're getting that loaded, I'm going to open up this Mathematica notebook. This is the file that you might be downloading. And here's the problem of a singular perturbation. It's this, we're going to start with a polynomial, second order, something you can solve analytically, something that is not very difficult to solve analytically. And all I did is I took the last one that we had, and I just moved the epsilon from this second term, which is multiplying the x, and now it's multiplying the x squared term. As I've said a couple times already, this is the hallmark of a singular perturbation problem. Whenever the small parameter multiplies the highest order term in a polynomial, that being the highest order polynomial term, in a differential equation, that being the highest order derivative. Whenever the smallest parameter multiplies the highest order term in your equation, you are going to encounter a singular perturbation problem. Let's visually look at what this means and what this looks like. So what I've done is I've created this fancy plot, which allows me to choose my epsilon and then kind of slide it. So if you load this up, it's going to say, this Mathematica notebook contains things that might be harmful to your computer. Should I enable dynamics? And you can click yes. This is something I made, so it's safe. And what that is allowing you to do is once you enable the dynamics, you'll be able to run these two lines of code. And so I'll run this one, and I'll run this one. And you can watch what happens as I take this. So what I'm plotting here in blue is this linear line, which represents this part of the equation that doesn't contain epsilon. And what is orange is the other half of the equation. So it's almost like I moved this thing over to the other side of the equation. I should be more clear, and I should be saying that really what I have is f of x comma epsilon equals 0. And so what I've done is just move these two terms that don't involve epsilon to the other side, which is why it becomes negative 2x plus 1, and then it's epsilon x squared. And you can see that as I change epsilon, you can see what happens. It spreads out this parabola. And what I really want you to look at here are two things. Yeah, perfect. What I really want you to look at here are that there are two intersections between these two curves. These two intersections correspond to the two roots or solutions to this polynomial. You'll notice that as I slide epsilon, one of the roots remains unchanged. It looks like it's going through 0, but it's actually not going through 0. It's going through something that's like around 1/2. But this root is changing location. So if you kind of watch this intersection of this outer part of the blue curve and this orange line as I change epsilon, you can see that the smaller I make epsilon, and you can see the number that's epsilon right here. The smaller I make epsilon, the further out this intersection point becomes. So it started out around -10, now it's out around -80. As I get even smaller, you can see it really quickly starts to drop. Now it's at -150, and I'm only at an epsilon of 0.01. That's not really even that small of an epsilon. If I get even smaller, 0.009, it looks like I don't have a root anymore, but that's just because I didn't extend my axes far enough. So you can imagine this would be intersecting somewhere around here. But when I take epsilon to be exactly 0, now I just have that being literally a horizontal line on the x-axis. There is no second intersection between that orange line and that blue curve anymore. It's gone. The problem changed from a problem that should have two roots. A second order polynomial should have two roots. A third order should have 3. A fourth order should have 4. This problem should have two roots. But as I take epsilon to be exactly equal to 0, I lose one of them. So why is this important? Well, if you think to what we're doing when we approach this problem with a regular perturbation method, the first thing we do is we solve the order 1 solution in which we take epsilon to be exactly 0. And so we're going to do that right now, and you're going to see that when I take epsilon to be exactly 0, I only find one solution. And so that's the problem. I should expect two solutions. When I take epsilon to 0, I find one solution. Okay, so let's look at this. Nothing about what I'm going to do right now is going to be new. So I'm going to show you This is my analytical solution. I can just solve my equation, so you can just run this, and it solves my equation. You kind of get a hint that something is a bit different here because of the appearance of our small parameter in the denominator, which kind of tells you that as epsilon goes to 0, this is going to blow up. It's going to go incredibly to large or positive or negative values. And we can plot this, and we see exactly that. So we see this strange behavior. So this strange behavior consists of our roots basically kind of hovering around something close to 1/2. One of them does. And then the other one basically jumps in magnitude dramatically the closer and closer you get to epsilon is equal to 0. So here we have something that starts out around -1/2. And as soon as epsilon gets to around, say, 0.1, we're already at a value of either positive or -20. And you're seeing this kind of asymptotically going to infinity as epsilon goes to 0. And this is the problem. This is what we're trying to resolve, is can we find these roots? These are the exact analytical solutions, so we know what they are. So our goal now is to see if we can approximate this. Once we get comfortable approximating something that we know the solution for, we can then move on to approximating things that we are unable to find the analytical solution for. Okay, so this is the analytical solution. We would like to turn around to kind of pretend we don't know it and see if we can approximate this. So I'm going to set up some general definitions. These should look familiar. I think for the sake of being concise, I changed this from expansion general to just guess, because it's our guess. But it's the same form. Summation of our variable sub n times epsilon to the n. I have to use this notation key to tell me that I can turn this into a symbol. I actually should probably do this twice. I think I will eventually use capital X, so we'll do that just in case. I don't think it matters though. Oh, yeah, it doesn't matter. And just to remind you, if I write guess x comma 1, so that's the first order, I get x naught, x plus epsilon times x sub 1. So this is all fine. This should be the same stuff you've done before. And now let's look at the regular perturbation. So we can take this out to order epsilon, order 1. So just like before, we take our, remember we have f of x comma epsilon, and what we want to do is replace x with our guess. So instead of writing x here, we write our guess, and we're doing this to order 1. So that means we take epsilon here to be exactly equal to 0. We send this into this equation. Now we still have an epsilon, and in this particular equation, we could just literally set that equal to 0 and just simplify it, but I'm just kind of doing this formally so you have the framework to do this for more complicated problems. So what we always do is we take our equation that we've got in terms of x naught now, and we do a series expansion. So this is just take a series of that equation, get rid of the order epsilon term that appears. I'm taking a series in respect with respect to epsilon around point 0 to order 0. So this basically just kills this term here, and I'm left with this equation. This is pretty trivial to solve. You can do it in your head. It's going to give me a half, and it's exactly what it does. If I solve for the order 1 thing, this is a bit unnecessary because it's going to give the same answer, but I just want to remind you that what you do when you have this, you've just solved for the prefactor x naught, and we need to put that prefactor back into our guess, and the end of it, at the end, it just becomes x equals 1/2. And we can plot our solution, and we see it does pretty well. So I'll make this big so you all can see it. So I made our our analytical solution transparent, so you can see how this curve sits on top of it. And you can see that it basically predicts that one of the roots is always going to be a half, which is not quite true, but it's pretty close for most of the time for most values of epsilon. But you can also see that it only gave us one solution. If we wanted two, we only got one. We expect there to be something else happening over here and here, but we don't see anything like that. So your first inclination could be, well, this is only the order 1 solution. Maybe I should take this out to order epsilon. Let's see what happens. So we repeat the same procedure. I'm putting x back into my f of x, but this time I'm going to put in my guess with x and to first order an epsilon, and I get this thing. So now you're seeing I have my equation with x with subscripts. I've got a bunch of epsilons in there. I need to make sure that I'm only retaining order epsilons that appear with an exponent of 1. The way I do that is I do a series expansion. Again, same procedure, very simple. We're just copying and pasting. And you'll notice that what I did is I inserted x naught, my solution at first order, in. So now my equation only has x1 appearing in it. The epsilon multiplies this equation. We know that epsilon can't be 0 because we just did that solution at order 1. So this thing kind of goes away, and I'm left with just a very simple equation again. This is also pretty straightforward to solve for x1. It's going to be -1/8. And now remember, here's the important point where you have to put in x1 back into my guess for x. My guess for x would be x naught plus epsilon x1. So I put in my guess, I insert x naught, I insert x1, and I get my equation, which looks like 1/2 minus some small varying parameter that is cut even smaller by dividing it by 8. So this is very weakly changing from 1/2, which makes sense. I mean, it looks like it's basically 1/2. And so we can plot this, and we can see what that looks like. And you kind of can't really see a difference. Maybe you can. Let's see. Let's make this thing bigger. Yeah, sure. So you can see that as epsilon gets larger to negative, larger to positive, it's starting to deviate. If we continued, what you would find is that if we took this out to order epsilon squared, order epsilon cubed, epsilon to the 4th, every single time we would be left with one solution. We would never find a second solution. And what would happen is this red curve would start to bend up. You would see this thing, so you can see over here, it's kind of bending up. It would continue to bend up along this way here to kind of capture this kind of bending that we're seeing in our root around -1. But we would never see or have any curve that starts to outline this blue data. And that's the problem that we're going to encounter today. That is the problem of trying to approximate the solution to an equation that has a singular limit as you take epsilon and get rid of it. What questions do you have for me? Any in the chat box?
I'm sorry if this is a stupid question, but in the approximate solution of order 1, why is it necessary to reiterate that f of x epsilon equals 0?
F of x epsilon.
Or I have as line 87, but
This then?
yeah.
Yeah, that was just for me to remind you all that our function that we define, it's kind of, I think what can happen is that it can be confusing as to like this line can look confusing. And so what I just wanted to remind you of is that this is the equation we're trying to solve, and we're replacing x with our guess for the solution. So this is completely unnecessary. Adding that does nothing. And
Okay.
mostly just to show you that what we're doing is, this is the equation we have, and we're replacing x with our guess for x. And that's going to lead to this new form of the equation here. So it's completely unnecessary. It does nothing to the code. If you delete it, your code will work completely fine. This is mostly just to illustrate that that's the equation we have. We'd like to replace x with our guess.
Okay. Thank you.
Yep.
Could you just explain that, like, guess definition, like where you defined guess and what that, I think it's line 7.
Yep. So what does that mean? Let's see here. So you can, let's take this thing out. Let's make this a little simpler. Let's say, let's replace var with x. Let's replace nn with 2. So this is just saying, do the summation. So that's going to give you that capital sigma sign. Summation of x sub n times epsilon to the n. Do the summation from 0 to 2. This is equivalent to, I feel like, I wonder if I could do this. This is equivalent to writing, like, let's see, it's going to work. Like that. I don't know how to do this in Mathematica. I think there's a way. N equals 0. You're kind of doing something like this. You're doing the summation from n equals 0 to 2. This is not the right notation. I can't remember how to do it. Of x of n epsilon to the n. So imagine like the n, you probably can't see this. Hold on, let me make this bigger. Imagine like the n equals 0 was below the sigma, and this was and the 2 was above the sigma, so you're kind of going from n equals 0 to n equals 2, and you're doing this summation. And so that's all that function is doing, is creating the ability for us to say, give me a power series out to whatever order I want in whatever variable I want. And I think the reason why the n is not working right is because I didn't run this thing. Yeah. All right, try that again. Does that not work? This does. I don't know. I think it has to do with the way that this is defined. Okay. So that's what it's doing. The idea is to say you want to create a power series expansion for our guess. Now, the general way to do that would be to have it such that we didn't really know what the exponent was, and we would be saying it's going to go epsilon to the alpha, epsilon to the beta, epsilon to the gamma. But for simplicity here, I'm just kind of assuming it's an integer power series starting at epsilon to the 0, which is basically what multiplies this term. I wish I could replace those. Yeah, let's do it here. Epsilon to the 0, epsilon to the 1, epsilon to the 2, 3, 4. So this is our way of saying, I think we can approximate our solution using a Taylor series expansion. This doesn't look exactly like a Taylor series, but if you go back through the notes, you can see that we went back and showed that these coefficients correspond to the 1 over n factorial times the derivative of x with respect to epsilon evaluated at epsilon is equal to 0. So this actually is a Taylor series expansion, even though it doesn't really look like it, or it's connected to one, I should say. I guess. Does that help? We're basically just assuming that our guess could be represented by a power series expansion.
Okay, and then down in like line 13, you basically are replacing your x in your f of x with that guess to that specific order.
Exactly. You can think of it this way. Is you can think of it really a better way to write this would be that I'm saying that x is equal to that.
Okay.
And so then I'm saying here I'm calling for x, and I'm going to replace x with the right-hand side of this equation. And so that's what this command is doing. It's saying instead of sending x, send in this x, which is our guess at the solution.
Okay. Thank you.
Just a quick question on that. What does the arrow notation do in this case?
The arrow notation thing, that is that issue. It allows this to be the only way I can say this is that it allows this to work the way you think it works based on having studied math. Like, if you don't do this, it treats x sub n as a variable, and it's almost like you just called it like xn. And we're saying we don't want x sub n to be a variable. We want x to be the variable and n to be a variable, and then we could kind of replace n with 1, but still not do anything with x. and we have different variables. So like, if I leave this without this notation here, it's almost like Mathematica thinks xn is your variable, and it won't ever replace n with your number here. Like I'm saying here, I want you to replace n with starting with n is equal to 0, then n is equal to 1. So it basically turns this into, instead of saying xn is your variable, it's saying x is a variable, n is a variable. You can send n different indexes, and then it'll treat that as a set of different variables. I don't know why that's not done by default, but that's in order to make this look like the notes in your notebook, you have to use this. You could get around this if you just wanted to, like, one of the notebooks I have from the earlier perturbation methods doesn't use this notation. If you don't like it, you can go use the other approach. I just was trying to keep this looking like the notes we did in class.
But why do you need the arrow notation right before this? Because I've seen you do this symbolized before, but I don't think I've seen that error.
Yeah, sure. You mean this notation I just highlighted? This?
Yeah.
Yeah, that's kind of like in like Python or C++, where you would ask it to like read in a library. Like it's almost like you're saying like read in this library of notation, and then once it reads in that library, you can use this command. And so it's equivalent to saying like in a C++ code like input header.h, or in like Python where I forget what the notation is, whether it's include or but it's like when you're importing a library that's kind of not in the typical like standard Python library. This is like importing the notation library that's not in a standard Mathematica library.
Okay, that makes sense. Thank you.
Other questions? So the problem is that in the way we've currently constructed these variables, our expression has epsilon multiplying the highest order, in this case, polynomial term in our equation. And that means we always lose this term as we take epsilon to 0. And losing this term is what causes us to lose that other root. So therefore, we can't get the entire solution. In an initial value problem or a boundary value problem, this is a really big issue, because what that typically means is that you might have, for a second order, say, ODE, you might have 2 boundary conditions or 2 initial conditions. If this small parameter multiplies the highest order derivative term in your equation, you lose the ability to apply all those boundary conditions. So you're not even actually solving the problem that you think you're solving, because you are unable to apply all the initial or boundary conditions. We need to kind of reformulate our equation in a way that we keep this term, even as epsilon gets really, really small. And that's the goal for the singular perturbation. We reformulate this equation, and the way we reformulate this equation is through a change of variable. So here's our change of variable. This thing I'm highlighting here is the crucial thing. We are always going to take a new variable. In this case, I called it capital X. If you want, you can call this, X bar, or X with a circle on top, or X with a hat on top. But it's a new X, so I'm calling it capital X. And our new X is going to be equal to our original X divided by epsilon to the gamma. This is always the change of variable that we're going to seek. And it kind of makes sense, because we want something where as epsilon gets smaller, our new variable gets bigger. right? Because the problem we have currently is that as epsilon gets smaller, we lose in a really, really important term in our equation. So what we would like to do is do a change of variable such that as epsilon gets smaller, that really important term remains in our equation and remains important. So this is the key thing here, which is why I'm kind of dwelling on this for a moment. So we're going to introduce a change of variable. We're going to call it capital X, and it's going to be equal to our small x, our original x, divided by epsilon to the gamma. Now we don't know what gamma is, and so what the next step in this process. So the first step is change of variables, and the second step is determine gamma through a dominant balance. And the second step is usually one that brings on the most confusion. So let's first start with this first step here. Pretty straightforward. I'm going to define that big X is equal to little x over epsilon to the gamma. I call that var change, variable change. And what I'm going to do is, just for clarity, I'm going to say, just for really making things straightforward, I'm going to say, let's just solve for little x. So that should mean multiply both sides of the equation by epsilon to the gamma. So I just literally solve this equation for little x. So I get little x is equal to big X times epsilon to the gamma. So now remember what I've done here. I'm going to be really pedantic here. Little x is equal to big X times epsilon to the gamma. And now what I'm doing is the same thing I did before. I'm going to insert little x into x for my f of x comma epsilon. And so that's going to be replacing little x with big X times epsilon to the gamma. So doing that, yields this equation here. This shouldn't be surprising. So now our term with that had the little x before. So let me just remind you. Let's compare this to what this used to look like. So what this used to look like was this. And so now our term that was linear in x is now linear in big X, but it's multiplied by epsilon to the gamma. And now we had this x squared term, which was multiplied by an epsilon. And now our x squared term, which is now a big X, is multiplied by epsilon. So this is the original epsilon, so that's the epsilon to the 1, plus 2 gamma. And it's 2 because we're squaring it, so this ends up being 2 times gamma. But we're adding exponents here, so we get epsilon to the 1 plus 2 gamma. Okay, so this is our new equation that we're looking to work with. This should be pretty straightforward. You can do this by hand, but with more complicated equations, it's certainly an easy thing to mess up. And so here's our new equation. And our next goal is to figure out what the magnitude of our exponent gamma is. And the way we evaluate the magnitude of our exponent gamma is through what's known as the method of dominant balance. Conceptually, the method of dominant balance, what this means is, let's think back to what our goal is with this variable change. Our goal with this variable change is to make sure that as epsilon gets really small, this term that has the x squared term remains large and doesn't disappear. So what we're looking to do is to find a value for gamma that ensures that as epsilon gets small, this term is a dominant term in our equation, which means it's a really large value. Whereas before, you recall, as epsilon got smaller, that term went to 0, so it was not a dominant term. It was taken over by these two terms. So our approach with this dominant balance is to make sure that this term stays, and we find a gamma that balances it with some other term in the equation. You'll notice that as we took epsilon to 0 last time, the two terms that were dominant were these two. Oops. These two. Now what we're looking to do is find an expression for gamma that makes sure that this term and one of these two terms remains in our equation. And so the way we do this is we kind of just check all the possible balances. In this case, there's only two to check. We have to make sure we keep term 3. And so we're going to balance term 1 in term 3 and term 2 in term 3. Term 1 being this one, term 2 being this one. Okay, the way we do this is we want to set, we come back to the equation that we're come back to our change of variable equation. We'll kind of remove this thing, so I don't want there to be any confusion. We are now working with this equation here. And the way we do this is we are going to determine gamma by balancing the exponents on each term. So let me show you what that means. So, okay, so let's do this line by line here. So let me copy this here. So the first term is, so this is my equation. The first term, it's just like a list like anything else. You can just say, give me the first term. And you just put the square brackets in the 1 and it gives you the first term. You can say, give me the second term, or give me the third term. Great. But we actually don't want the whole term. What we want is the exponent of the term. And we have to tell it what exponent in particular we're interested in. So we're actually interested, the first term was 1, I think -1. So we're interested on the exponent on the number 1, which is just going to be 0. Right? And next we're going to look at the exponent on this third term. So again, this is my equation, the third term. Give me the exponent. The exponent we're interested in is the exponent on epsilon. I wonder if this works if I say epsilon here. I think it does. Yeah, it does. Okay. So I could have made the exponent on epsilon for all of them, which is really what we want. Let me try and do that. There we go. The exponent on epsilon, as you can tell just by writing it down, is 1 plus 2 gamma. You can just obviously observe this. You can do this by hand. I'm just doing this in Mathematica, so we don't have to bounce back and forth with our notebook. But we're basically saying that this, can I highlight that? Yeah. This thing and this exponent have to be equivalent to each other. And so we end up with this equation. So the exponent on epsilon, well, there is no epsilon, so the exponent is 0. So the left-hand side is 0. The exponent on the right-hand side is the exponent on my third term, which is 1 plus 2 gamma. So I have 0 is equal to 1 plus 2 gamma. The goal here is to pick two terms, set the exponents on epsilon equal to each other, solve for gamma. That's all we're doing. So this gamma, I call it gamma test 1, is solving for gamma. So I'm just solving this equation. So I copied this whole thing, and I put it inside this solve here. Oh yeah, I changed this to epsilon, sorry. And I'm solving for gamma. There's only one solution, so it's going to give me one solution. So let's run this. And it's -1/2. This part is generally quite confusing all the way through, so I'm going to kind of ask for questions often and early. Are you with me so far?
Could you repeat why you're balancing the first and third term and not like the second and third, or does that come later?
Yeah, so there's only 3 terms in this equation. We have to keep the third term. And so that means we have to test two options. One is balancing the first and the third, and the other is balancing the second and the third. Arbitrarily, I picked to do the first and the third first, and then we will do the second and the third term next. If there was 4 terms, we would have to do 3 balances. The key thing here is that we always have to keep that term that we want to remain, which is that term that has the x squared. And so the third term is always going to be there for us in this case. And we're just picking to balance it with the first and checking, see if it works, which I haven't explained yet, and then doing that whole process again for the second term, and then checking to see if it works. Good question, though.
So will we always just set the exponents of the epsilons equal to each other since they're the ones that are going to have the gamma?
Yes.
Okay.
And if it's confusing for you, you can imagine that this first term here is really like -1 times epsilon to the 0. And you still, and epsilon to the 0 is 1, so you end up with the same term. So if that idea is confusing, that you're balancing terms, or some of them have an epsilon, some of them don't, then just kind of rethink the problem and say, okay, well, this is kind of like -1 times epsilon to the 0, and so now I have epsilon on every term, and I can just make sure that I'm balancing their exponents. Okay, what we do now is we found gamma. So if this is the correct balance, then we know that gamma should be 1/2. We can take our equation and insert gamma of -1/2 in for gamma that was in the exponent of epsilon, and we end up with this equation here. This is the point where I think confusion seeps in. What we have to do now is determine if this is a consistent balance. What I mean by that is, as epsilon gets smaller, do we retain the terms that we want? Are the terms that we want to keep dominant, and what I mean by that is, are they large compared to the other terms? Or are they going to suffer the same fate as they did before, which is that as epsilon gets smaller, we still lose the term that we're interested in? Okay, how do we do that? So this term here and this term here don't contain an epsilon in them. So they're of order 1 always. No matter how much we change epsilon, these terms are always going to be of order 1. This is literally 1, -1, but we're looking at absolute values here for determining kind of the order of these terms. But this term is going to vary as I take epsilon to different values. And I'm going to show that by plotting it. So these terms are both kind of order 1. You could think of this as, if it's confusing that they're order 1, you could do the exact same thing we just said and say, well, this is the same as saying this is -1 times epsilon to the 0. And this is like epsilon to the 0. And this is like root epsilon, or 1/√epsilon. And so this is of order 1, this term is of order 1, and this term is of order epsilon to the -1/2. And so what I'm plotting here, I guess I'll do this just for clarity. I'll call this epsilon to the 0, and I'll call this epsilon to the -1/2. So the blue curve is going to be the magnitude of this term and the magnitude of this term as we vary epsilon. And the orange curve is going to be the magnitude of this term as we vary epsilon. So here's a log-log plot trying to illustrate what happens. Remember, we want this term to be dominant and large as epsilon goes to 0. Because in the original case, as epsilon went to 0, this term went away. And now look what happens. we have the same problem as we did before. As I take epsilon to 0, clearly this term doesn't, these two terms aren't affected. They're both of order 1. And this last term, which is of order epsilon to the minus 1/2, really starts to increase in magnitude the smaller our epsilon gets. So we can make this even, let's see here, we can make this more clear. Let's go to smaller, I don't want that. Let's go to smaller values. 0.01. The smaller I take epsilon, the larger this term becomes. And these terms are still not relevant. They're incredibly small. If you're imagining like, I'm trying to, these numbers should all add up to 0. This term contains the large magnitude term, and these terms are basically 1 or negative 1. This term is getting larger and larger in magnitude. These two are not. So is this a consistent balance? The answer is no. The reason why it's not a consistent balance is because this term is irrelevant as epsilon gets smaller, and we want this term to be dominant as epsilon gets smaller. So this doesn't work. This solution for gamma being 1/2 or negative 1/2 doesn't give us a balance in which we retain that really important term. We have a problem in which we still lose this really important term here. What questions do you have for me? Does this make sense? Does the graph help? See if there's any chat. This probably will make more sense as we go through the next balance. So it's probably easier to understand why this doesn't work if I can show you what happens when it does work. So let's move on to the next balance. Let's put a pin in this for just a second and say, okay, that looks like that term is always small compared to this term, and we didn't want that. So let's kind of look at our third option, or I guess our second option, which is balancing the second term with the third term. So I'll remind you, the second term in the expression, well, let's do it again. This is our expression. The second term is this one. The third term is this one. So we can be really clear about that by saying second term, that one. Third term is that one. I'm looking for the exponent on the epsilon term here. It's the same. And I'm looking for to balance that with the exponent of the second term, which is gamma in this case. So when I balance those two things, I end up with an equation that says gamma is equal to 1 plus 2 gamma. And now my second test for gamma is to just solve this equation for gamma, which is very straightforward to do. I'm kind of doing it out in Mathematica speak just for clarity, but it's just equal to negative 1. And so now we can replace gamma with negative 1 in our original equation here. And I'll do this again for clarity. You can think about this term as being really epsilon to the 0 plus 2x epsilon, 2x over epsilon, and x squared over epsilon. So two terms have the same relation to epsilon. Again, these two terms both go as 1 over epsilon, and this other term just goes as order 1. So now when I plot this, the first term is this 1 over epsilon response, and that's going to be colored in blue. And the second term is my epsilon to the 0 term, which is going to be of order 1. It's always 1. I plot this, and now you can see as epsilon gets smaller, these two terms completely dominate the balance in terms of their magnitude. The smaller epsilon is, the larger the magnitude of each of these terms are. And this term is really negligible compared to those higher terms. These are terms of order 100. This is term of order 1. Add epsilon is equal to 0.01, I should say. So the smaller epsilon gets, I retained this term that I want to keep, and I've retained this other term here. This is a consistent balance because we've chosen a value for gamma that rescales our equation in such a way that as epsilon gets smaller, our highest order term remains. I'm going to say that again. We've rescaled our equation in such a way that as epsilon goes to 0, now our highest order term doesn't disappear. It remains a dominant term in our equation. That means we'll always have a second order polynomial, which means we'll always be able to find this alternative solution, the one that we've been missing. Now let's talk about this method of dominant balance. What questions do you have?
Is it possible that you can't find the consistent balance?
I've not encountered that case. A possibility that is unlikely and you're quite unlucky if this happens, is that no term can be neglected when you're trying to make an approximation. So maybe you have a really complex set of equations with multiple terms in there. A possibility is that none of those terms are small relative to others, although it's really rare. But that doesn't mean you won't find a dominant balance. It just means that you won't be able to simplify your equations by neglecting those negligible terms, because there are none. But again, that's something that I also don't encounter, or I can't recall encountering. There should always be a dominant balance that allows you to rescale your equation such that you can kind of maintain the terms that are important in this rescaled form. You should always be able to kind of like renormalize or rescale your equations in such a way. From that point on, you might have some difficulty simplifying your equations to the point where you might still have trouble solving them, but you should always be able to rescale them. So I think you can always find this balance. I don't know of a case in which you can't. It's a good question, though. So what do? Well, what we do now is we have a new equation that we want to perturb and approximate. And we do this in the same way that we've been doing things before. So now we have our new equation. I'm calling it equation for capital X, so equation capital X. And that new equation is going to be my original equation, in which I substitute in my change of variable, which is what I've highlighted. And then I also substitute in my known quantity for gamma, which is that gamma is equal to -1. So I get this equation that I wrote up here before. So it's the same thing. Now what I'm doing is, just like we do every time with these perturbation methods, we want to replace capital X with our guess for capital X, being capital X is equal to x naught plus epsilon x1 plus epsilon squared capital X2, and so on. And so I refer to this as my singular equation order 1, which is give me this equation, which is this thing, equal to 0, and replace capital X with our guess. And the guess to order 1, or in this case, which means epsilon is 0, the exponent on epsilon is 0, is equal to basically the same exact equation, except now we replace our x's with x naughts. if you were doing this on your pen and paper, what you would do is just multiply both sides by epsilon and just kind of make your equation simpler, because what you would want to really be able to write is that like negative epsilon plus 2 x naught plus x naught. There we go. What am I doing? There we go. What we really want to do is just rearrange this equation to look like this. And now you can kind of see more clearly that this is a regular perturbation problem, right? So this is a little bit of a confusing equation just to look at. You're not used to seeing that kind of epsilon appearing in the denominator. But if we just multiply both sides by epsilon, you see pretty clearly that this is a regular perturbation problem. I have an epsilon. It's not multiplying the highest order term in my equation. And then I have these other polynomials. So I should expect to find multiple solutions here. And to get Mathematica to do that multiplying both sides, you have to do things that you assume and take for granted, but Mathematica won't, which is that we're assuming when I multiply epsilon on both sides of the equation here that epsilon is not equal to 0. If it was, that's a problem, because this would be singular here. And so you have to tell it that. So you can kind of ignore this thing if you, or you can kind of look into it if you want. But I'm basically just rearranging this equation to make it easier for us to see what we're doing. So rearranging it by assuming epsilon is not equal to 0, then multiplying both sides by epsilon. You can do this on pen and paper much quicker than you can in Mathematica. And now we can take this equation. The reason why we're doing it, so you might be like, well, why is he doing it at all? Like, I don't really care. I trust that it's a regular perturbation. The reason that we're doing it is we need to have this epsilon term here if we're going to do a series expansion. If you try to do a series expansion with that epsilon in the denominator, Mathematica, for some reason, doesn't do it. I haven't figured out why yet. So multiplying it to make it into this form, or like this form, if you will, allows you to just simply do what we always do, which is do a series expansion so that we make sure we only retain terms of epsilon to the 0. And then we have a very simple equation to solve. And we can just solve this to find out what x naught is. X naught is -2. We do the exact same stuff we did before, which is we replace our guess with our known exponent, which doesn't really do anything here because our guess is the 0th order, so it's just x is equal to x naught, so it's the same thing. However, the next step is really important. The next step is we actually want to compare our solution for x with our, what we know is the analytical solution. But right now we're dealing in the change of variable space. We're dealing with capital X. And what we need to do is work with our original variables again. So we have to change back. So what that means is we have to say, okay, this equation here is our way of saying that x is equal to -2, right? Because initially we're saying x is equal to x naught plus epsilon x1 plus ... But we're looking just at the order 1 solution, which means we take epsilon to 0. So we are left with this. This thing here is this. And so what we'd like to do is to take this equation that we have here for our solution and then replace x with our change of variable of x over epsilon to the gamma, but gamma is equal to -1. And that looks like this. And solving that for x is trivial. You just divide both sides by epsilon. And you get our singular solution, which is that we end up with little x. So you can really read this equation as like little x is equal to -2 over epsilon. Who's confused? Give me some questions.
Can you explain again what you did in your in62? So like right before you like substitute your change of variable and solve for little x.
Yeah, sure. So I do this just to be extra careful. I want to recall this equation here. Oh no, why did I put that? Okay. This equation here is saying is solving for the prefactor x naught. And so now we have the, or the coefficient, or maybe this is easier to think of, or the coefficient on epsilon to the 0. And the reason, and so now we're saying that, okay, we've just solved for x naught, but we need to recall that our guess says x is equal to x naught times epsilon to the 0 plus x of 1 times epsilon to the 1 plus x of 2 and so on. So, oh gosh. So this thing gives me this quantity, and then just for the sake of there not being any confusion at higher orders, what I'm saying is you really should remember that you're actually just taking this quantity that you just found and putting it back into our guess. So our guess to order is that, and so now we're just saying replace x naught with what we just found for x naught. Does that help? At this order here, it doesn't matter. Like you could literally just go with this one. It's always going to be the same number. However, if you're like writing a program to do this, you would mess it up because you need to always take the coefficient and stick it back into the guess. And then you start solve it at a higher order, find the coefficient, stick it back into the guess. At first order, it yields the same result. So it's a little bit silly, but I feel like it's kind of silly, but will lead to less mistakes in the future.
Okay. Yeah, that makes sense.
Other questions? This part is really confusing, so I don't want to rush through it because I think I'm throwing a lot at you.
I don't know exactly how to word my question, but I think I'm getting a little confused about like using the series in line 60 versus the guess. And I don't know if it's just because they're both like expansions where we're taking epsilon to a certain order, but like in line 60 where you're doing the normal series, I guess, like what exactly are you doing there and what's the point? Because I see you're replacing your guess at order like 1 into there, but then yeah, I don't know. I guess I'm just a little confused on that. It's not a great question, but I don't know how to word it.
It is a great question because it's always confusing because we do a series expansion twice, and that is always confusing. So let me remind you of what we're doing. And so it's probably easier if I go way back up to the top. So our guess is a series expansion. So this is the first point I want to make. Our guess is always a generalized Taylor series expansion. Here we're looking at a power series because we're assuming the exponents on epsilon are integer order. So this is our guess for the answer for x. We are then going to insert our guess for the answer to x into our equation for x. Okay. What that leads to, and you can see it here. So here's our probably easier at first order. Let me show it to you at first order. So yeah, so let me remind you. So here's our guess. This is our guess. We're saying that x is equal to that. So we're saying that we're going to pretend that x is equal to this thing. And now what the key reason why I'm showing you this is I want you to notice that our guess contains an epsilon. Okay. So now we to get this guess, we've done a series expansion, right? We've taken out to various powers that are the exponents on epsilon. We took it out to order 1 here. And we're inserting that into our equation. And the result of that, so just taking this and replacing x, which usually is right here, with this guess, it gives us this new equation. Now here's the key thing. We've used one series expansion to represent our guess. It leads to the appearance of this epsilon term. If we took this to higher order, it would have an epsilon squared term. We're inserting this solution for x into our equation. And now what you see is that the new equation that we want to solve, the second term contains an order epsilon term. This term, let's take it and expand it. This term contains 3 epsilon terms. So in reality, this equation is like awful. So this is and so what we are trying to do is we're trying to say the only way that I can solve for all my coefficients is to solve them one order at a time. So I first solve them at order epsilon to the 0, and then I solve them at order epsilon to the 1. To solve it at order epsilon to the 0, I have to take my equation and get rid of any terms that contain epsilon. To solve this equation at order epsilon to the 1, I have to take my equation and get rid of any terms that contain epsilon squared or higher. So you can see that by inserting this guess into our equation, our new equation contains an epsilon squared term and an epsilon cubed term. If you're doing this by pen and paper, you could just literally scratch out those terms and just solve what remains. If you're doing this in Mathematica or any kind of coding where you want to systematically retain only the terms up to order epsilon, then what you do is you do another series expansion. So we take this thing, not this thing, we take this thing, and we do a series expansion of it. I see everyone that the chat is blowing up. I will get into those questions in just a second. And we do a series expansion of around epsilon, around 0.0 to first order. And that truncates this series to only contain epsilon terms. And then we can tell it to get rid of that annoying thing at the end. And now our equation that we want only contains terms that have order epsilon or lower. So the first expansion is to provide our power series guess for the solution. The second expansion is to take once we've inserted that guess into our equation, it truncates that equation at the order that we're trying to solve it at. In this case, it's order epsilon. Does that help?
Yeah, that makes more sense. Thanks.
Okay, let me jump onto the chat and see what's going on here. Okay. Yeah. Okay, it looks like there's a question about why do we choose gamma is equal to -1. It looks like that was being talked about in the chat, but I assume that if one person has that question, multiple people have that question. Is the idea of the dominant balance making sense? What questions do we have on the dominant balance term? Conceptually, what the dominant balance should do is we've changed our variables, and in that change of variable, we've introduced an unknown parameter, gamma. And that unknown parameter is kind of it's kind of a way of saying, like, how do we want to rescale our variables? And really what we're saying is, how do we want to rescale our variables in such a way that this important term doesn't disappear and become negligible when epsilon goes to 0? So we have two options to try to balance that unknown gamma term. The first is to balance it with this term, which has multiplied by epsilon to the 0. And if we do that, we find a gamma of -1/2. And then plotting this, we see that the epsilon to the -1/2 term, which I will point out multiplies the x term, not the x squared term, the x term, becomes significantly bigger than these other two terms, which are on the same order. So these are both epsilon to the 0, this one's not. And the hope is, since these are balanced, so these are epsilon to the 0 because we forced them to be the same. We said balance the exponents on those two terms. This, if you recall, was term 3. It got rearranged, sorry. This is term 1. So what we said is we forced those terms to have the same magnitude on epsilon. That's why they both have epsilon to the 0. We made them balance each other. And our hope was to find two terms that balance each other that are always larger than the third term when epsilon gets smaller. And here's what we have. These two terms balance each other, so check, we did that right. This term doesn't, it's of a different epsilon. So our goal is to say, well, as I take epsilon smaller, are these terms larger than this term? Here's the plot of that. The orange is the term I have highlighted, and the blue are these two terms. The orange one is always significantly larger than those other terms as epsilon goes to 0. So this is not a good balance. These terms are both negligible. So we don't keep that. We can return and balance the other two terms in our equation. That yields, again, you'll notice I'll be kind of really overly detailed here. These two terms both contain epsilon to the same value, epsilon to the -1. These two terms are balanced because we forced them to be balanced. Now so the first step in this dominant balance is balancing two terms in the equation. The next step is checking to make sure that the balance that we found is dominant, meaning that the magnitude of these terms is significantly larger than the magnitude of the remaining terms as epsilon goes to 0. And so we do the same thing. We plot these. In this case here, the blue curve is the magnitude of these terms, and the orange curve is the magnitude of this term. And I'm showing how that magnitude varies as epsilon goes to 0. And clearly, the magnitude of these terms is significantly higher than the magnitude of the other term as I take epsilon to 0. And so this is our dominant balance. This is the correct solution for gamma. And then that's why we go back and kind of properly rescale our equations, knowing what gamma is, which is what we've done here. Does that help? Let me see if I'm missing any chat. All right.
Professor, so if we are calculating a more complex system, for example, the highest power to x is not is cube or of course, or yeah, even higher. So we need to compare the terms, and so is there a possibility that see epsilon, we have different how to say, so we have two different solutions to apply to the perturbation?
So that's a good question. So you're right. At first, you're right in kind of recognizing that as we get to higher order polynomials, a couple things happen. One is the higher order polynomials we have, the more roots, and therefore kind of solutions that we're looking for. I think Euler's number tells us how many of those roots should be real for polynomials and how many should be imaginary. The challenge when you have more terms and higher order polynomials in the problem is mainly one of you have to check this balance, maybe 3 or 4 different terms that you'll be balancing with to find the one that's consistent and dominant. This is primarily tedious and maybe a bit confusing, but I'm just going back and checking through some of my older notes. You kind of end up with a like a table almost of possible rescaling values for gamma that you're looking to see which one's consistent and which one's not. You will, if you do your balance correctly and you kind of evaluate the terms correctly, you will still end up with being able to say, nope, look, gamma is this value. This ensures that these 2 terms remain and the other terms can be neglected. So you'll still be able to find one. It's just a more tedious process because you have to evaluate maybe 3 or 4 different balances in there. Trying to think what other confusions emerge when you have these higher order terms. Primarily, the other confusion that pops up is something that we don't see here, which is, here we ended up with an integer as our gamma, and so our solution that we're going to find in a minute kind of still follows the same like power series form we expected. It goes from like epsilon to the -1 to epsilon to the 0 to epsilon to the 1 to epsilon to the 2, and it looks just like our power series, except that now instead of starting at epsilon to the 0, we started at epsilon to the -1. One of the things that can get more confusing is when your epsilon is actually, say, 1/2. And now your power series is going to be something like epsilon to the 1/2, epsilon to the 3/2, epsilon to the 5/2, and so on and so forth. I don't know if I'm answering your question well enough. I went down this road in previous iterations of this class where we did some more complex polynomials, and it primarily led to a lot of extra work and without a ton of extra understanding. And so I'm kind of hesitant to do that again. I think it's more useful for us to see how these apply to like differential equations and some of the more interesting kind of ways you construct models that way. But I can kind of point you in the direction of playing with the higher order polynomial equations if people are interested in. It's kind of more work and more like searching for a certain number of real roots in certain regimes, and it's a little bit tedious at times, but it certainly can be really interesting too. So I don't know if I'm answering your question, but
that helps a lot. Yeah, thank you.
Is everybody comfortable with what we did here, which is, up until this point, it really just looks like a regular perturbation approach again, except our regular perturbation was now for the variable capital X instead of the variable lowercase x. And so then we have this one extra step of saying, well, actually, I don't really want my answer to be capital X. Like, I need my answer to be in the variables that I'm interested in, which is lowercase x. And so I have to do one last step in substituting in. So after I have my guess, I have to substitute in and say, oh, actually, well, hey, just remember, I need to find this for lowercase x, and capital X is a function of lowercase x, and it's lowercase x divided by epsilon to the -1. And so I do this final replacement here to find my singular order 1 solution. And so at lowest order, our singular solution looks like -2 over epsilon. That's a way of saying that one of our roots was a half, and the other of our roots was actually -2 over epsilon. So let's look at what happens here. Let's plot this. Let's show our plots. And here we go. We actually have two solutions now. The first solution remains from before. You can see the gray and the red dots for the different orders of our initial regular perturbation. But now you see the appearance of our singular solution, which nicely actually captures the response really close to epsilon quite well, and then doesn't capture it too close to when epsilon gets larger as well as it did before. So now we're a lot closer than we were. We can repeat all these steps. We can do everything we just did again. We can say, let's take my equation, let's replace x with our guess, but this time let's do it out to order 1 instead of order 0. Do that. Let's do that thing where we multiply both sides by epsilon to help make the equation easier to work with. So I just say, hey, assume epsilon is not 0, and then multiply both sides of this equation by this value, which is multiplying both sides by epsilon. And I end up with this. And I do the same process. It's all kind of copy and paste at this point. So again, I have the same problem as I had before, where in my new equation here, epsilon is appearing at all sorts of different orders. I have a squared term here. So I have an epsilon squared over epsilon. I have an epsilon over epsilon. I have a 1 over epsilon. So I'm going to do my series expansion out to order epsilon to the 1. And I can solve this equation. This is pretty straightforward. As you recall, I know epsilon naught. It was -2. So I can insert for capital X naught with my order 1 solution, and then I can solve for the only unknown in this equation, which is the coefficient x sub 1, and I get that x sub 1 is equal to -2. And then here again, you have to remember, once you find the coefficients, you have to go back to your guess and insert the values you have for each coefficient. So you insert in x naught, and you insert in x sub 1. Now my equation to the next order in epsilon looks like this: -2 minus epsilon over 2. This is why, and this is a point of maybe like nomenclature, this is why I call this the order epsilon solution, because in my rescaled value, this is of order 1, this is of order epsilon. However, when we do the final step, which is replacing capital X with my lowercase x, so this is exactly like we did before, then I get a more complicated solution. So I'm going to go back and kind of undo our rescaling of variables. And I do that, and I end up with the order epsilon solution, but in my lowercase x variable. So this is basically like little x is equal to this. And now I can plot it. And you can see what's happening here is that at small epsilon, everything looks the same, which is great. We expect that our value, that our solution will deviate as epsilon gets bigger, which it does. My purple data is the new one. My blue one is the old one. So the purple one's closer, but it really starts to deviate kind of in this region over here. But you can see that this purple one starts to intersect with this red curve at a different point. So the blue one intersected with the red curve maybe over here. The purple one intersects with the red curve somewhere over here. Now these are both at the same order. What's going to happen is, as I continue to solve these up to order epsilon squared, this data is going to match this curve better. This red curve is going to shift up to match this curve better, and they're going to kind of start to coalesce at a point here. because if you're a step ahead of me, you will look at this equation and say, hey, wait a minute. Once epsilon is equal to -1, this thing blows up. Like this thing goes into an imaginary number. Once the epsilon is larger than -1, I have the square root of a negative number. I get some imaginary root appearing. So how come those approximate solutions are giving me things over here? And that's a really good question. And what happens, and this will become more clear in the next lectures, what we have to do is take these solutions, one that is from our regular perturbation and one that's from our singular one, and we have to match them so that they meet up together and they come. They're kind of like, it's almost like the red curve is bending up to that little point here, and the blue curve is bending down. And we know that if we took an infinite number of terms, those things would intersect right at that point. And so what we have to do is do some extra math to help match the solution that's matching the bottom root to the solution that's matching the top root, so that they intersect at this point and we properly characterize the roots of the system. Does that make sense? I'm kind of getting a little conceptual there. Let me check the chat. Do we need to do the first general perturbation method to obtain the solution that follows the orange line? So that's a good question. The chat question was, do you need to do the first general perturbation method to obtain the solution that follows the orange line? And I think the answer is no. And I think if you had just done the rescaling, and if you had not assumed any knowledge of x naught, then what you would have done is found two roots, and I think those two roots, one of them would have been a root at x naught is equal to -2, and the other one would have been a root at x naught is equal to 0. And I think, if I'm not mistaken, that basically one of those two roots is identical to the regular perturbation, and then the other one is the one we just found for the singular perturbation. So I think you could, and maybe this would be an exercise to try to solve this problem just doing the singular approach and see if I think you would get both solutions that way. And so it almost seems like if you don't substitute in what we know for x naught, I think it almost seems like you get two solutions in doing the singular one, but it's just, so it almost seems like you have three solutions, which doesn't make any sense, but two of them are the same. The one from the regular perturbation and one of the ones from the singular perturbation are the same. So I think the answer is no, you don't need to. You could still get it from the singular solution. But I would want to double check that. Maybe that's a fun exercise. Two answers. Yeah, exactly. Yeah, so it should have two answers. We took the first one. I probably skipped that step. Yeah. Yep.
Sorry, could you explain that again? I didn't fully understand it.
Yeah, I think if you if you do the singular solution, you should end up with two roots. One of those roots is the -2 one. Let's find it. Let's see where it is. So yeah, here. Let's do this one. I'm gonna try this here. Yeah. Okay. Cool. So this actually, sorry, I skipped this. I didn't realize that I pulled the first one. If you just solve the singular solution, so this is the second order polynomial, it should give you two roots. And pretty clearly, the trivial root is that x naught could be 0, because I just have x naught in both terms, so 0 is equal to 0. And the other one is the one we used. I skipped dealing with this root, it looks like now we have 3 solutions, one in which we solved in the regular perturbation, and now 2 coming from the singular perturbation. But this solution here is equivalent to the one from the regular solution. We would have to do a little bit of work, I think. But I think if you kind of just do a little double checking, you can confirm that this solution here is once you do the rescaling of variables and put it back into that normal form again, I think you would find that this root that we found here is equivalent to the one that we found from the regular perturbation. So that's a really great question, Susan, and thanks for pointing out that I kind of buried that there. I totally forgot that I did that. But yeah, this is a second order polynomial. It's going to give you 2 roots. That makes it seem like we have 3 solutions when in fact we really have two, and 2 of the 3 solutions are equal to each other. So you'll probably have to, I wouldn't say trust me on that, but I think you can go back and kind of see if you can rework this and convince yourself that the second solution is actually equivalent to the one we found before. Cool. Yeah, sorry for that kind of confusion. I forgot I did that. I don't know if we wrote this out, but I think we did. Yeah. Yeah, that's kind of the introduction to this topic. To sum up, you can identify a singular perturbation problem pretty quickly usually. And you can identify it by observing that the small parameter in your problem either multiplies the highest order derivative or multiplies the highest order polynomial. And the reason why it becomes singular is because when you take that small parameter to 0, you lose some of the solutions that you would expect to your problem. In the case of a polynomial, you're losing the number of roots that you would expect for the order of the polynomial given. In the case of a differential equation, if you have a second order ODE with 2 initial conditions, you will lose the ability to apply one or more of those initial conditions to your problem. And so the fundamental nature of it changes. So first step is identify it as a singular problem. The number of solutions that you would expect is different than what you end up with. The second step is do a change of variable. And your change of variable always looks like replace your independent variable x with your independent variable x divided by epsilon to some unknown coefficient gamma. At that point, you're going to kind of insert that into your original equation, and then you're going to apply the method of dominant balance, which means find the term you don't want to lose and balance the exponent on epsilon with the exponent on epsilon in each of the remaining terms, kind of one by one. Then you'll balance it, so you should end up with your original equation, which in this case had 3 terms. 2 of them have the same exponent on epsilon now. 1 of them won't. And then the way to check if your balance is a dominant balance is to check if the 2 terms that have the same exponent are larger than the other term as epsilon goes to 0. In this case, when we balanced 2 of the terms, the first time we did a dominant balance, we balanced 2 terms. We were able to find a balance so that epsilon went to the 0, epsilon to the 0, and epsilon to the -1. And then we found out that the epsilon to the -1 term is always larger than the epsilon to the 0 term as we take epsilon to smaller and smaller numbers. So that is an inconsistent balance. Repeat the process. Balance 2 different terms in the equation, remembering that you always want to have in your dominant balance the term that you're looking to keep. that term that is important, the term that you were losing before. Check to make sure after that balance, now you'll have that term and another term will have the same exponent on epsilon. And now your goal is to check to make sure that those terms are always larger in magnitude than the other term in your equation as epsilon gets smaller. When you find that value of gamma is the appropriate rescaling of x. And now all you have to do is insert that into your new equation with your rescaled variables. Do your perturbation approach just as you've done before to order 1, order epsilon squared. And then finally, your last step is to recognize and remember that you've rescaled your problem. And so then you have to go back and kind of undo that rescaling to put it back in terms of what you want, which is little lowercase x is going to be equal to what? It's going to be equal to 2 things. And that's the general approach to these problems. There's one more approach that we've kind of hinted at, not approach, there's one more step that we've kind of hinted at but we haven't done, which is recognizing that this solution in red and this solution in purple, if taken to infinite orders in our expansion, should coalesce at this point right here, where those two curves kind of bend together. And what we will end up doing is matching the solution from the red curve to the solution to the purple curve, such that we end up with one functional form that describes that crazy, like swooping, I don't even know what shape that is, that shape, such that we don't have an approximation that says that these are solutions, because we know they're not. We can look at the polynomial and say, well, I know that if I take epsilon larger to a value below -1, that my square root's going to go imaginary. I'm going to lose my real roots. So these can't be real solutions here. We are going to address that. We're just not going to address it today. We'll address it in our next lecture. That's, if you've ever done any reading in or encountered any applied mathematics, what we're next talking about is what's referred to as matched asymptotic expansions. Because these are asymptotic expansions. We are trying to solve for our approximate solutions as we expand these things out to higher and higher orders in our small parameter. And we're going to be matching these asymptotic expansions. Here we have kind of what looks like one solution and a second solution, but in reality, this should just be one solution that is kind of matched together. And that will take us some time to figure out how to do, but that's what we'll end up doing next. I'll try to go look at the homework and see if I can send some stuff out to you so you can start practicing this. I don't want you to have to wait. I had initially designed the homework so that you would approach it after you had seen all this, but I'll go back and give you some stuff to work on just so you can get comfortable applying these methods. In the meantime, like, go here and just like change this polynomial. Like, you can literally just say like, all right, I'm going to do this with like 4x, and like, you can make this, you can make it even more complicated. You can say like, I'm going to make this like epsilon squared 4x epsilon, and can I solve that? Or I'm going to make this like epsilon squared minus epsilon. Like, just as long as you don't change the order of the polynomial, like, you still have a second order polynomial, you can still solve it analytically. Like, you should be able to play with this. I don't know. And test that you can apply these methods. So you don't have to do anything. You should really be able to kind of run through this notebook without changing much at all. And you can kind of see what's happening to these solutions and your approximations as you play with this initial polynomial. Yeah, one more question here.
All right, so I actually have 2 questions. So the first one basically has to do with the balancing.
Mm-hmm.
And I mean, you kind of talked about higher polynomials, but maybe more generally. So if we have, say, 4 terms that we're dealing with, we're going to be matching 2 of them in terms of exponents. And then I assume that still our highest order, our x squared in this case, will have to remain large compared to the other 2 terms.
Yes, that's correct. So I'm going to repeat that for everyone. So here we had a simple problem in which we had 3 terms. We would balance 2 and compare those 2 terms to the magnitude of the remaining term. If you have like a more complicated polynomial or equation that has more and more terms to it, you'll do the same process. You'll pick 2 to balance them, and then you'll end up finding a gamma. And then you'll need to compare the terms that you said are the dominant ones with all the terms. So instead of having 2 graphs where I had one line that represented the 2 terms that were balanced and one line that was the other, you might have 3, 4, 5 curves. If you're not a visual person, you can do it in your head by saying like, okay, I think as this one goes to 0, this value should go up. But if you're doing this visually, you'll end up with kind of checking to make sure that the 2 terms that you say are dominant over all the other terms in your equation after you've done that balance. So yes, it would just have more kind of terms you have to check.
Okay, great, yeah, that makes sense. And then my second question is basically the discussion of the kind of looks like we solved 3 roots, but 2 of them are equivalent. Mm-hmm. Honestly, just me doing this, maybe it wouldn't be so obvious whether, like, which one of the 2 solutions from the singular is the new one, the non-repeat solution. And so I guess, like, if I were doing this, I probably would just use the 2 solutions that I got from the singular, and like, you know, then I don't have to worry about which one of them is the repeat, you know.
Yeah, and so I will always kind of back up and remind you that like the end goal of this course is not for you to be able to do like homework assignments efficiently on these types of things. Typically what's going to happen is you're going to have like one equation that you need to approximate. And you're going to try 6 different things, and you're going to try, I'm going to do the regular one first, then I'm going to do the singular one, and then I'm going to check. Then I'm going to just do the singular one and see if I just do that, do I get all the same stuff? It's kind of like double checking your work. So like, I want to remind you that my goal is not for you to be able to like be handed a singular perturbation problem and like solve it efficiently as possible. My goal is for you, when you encounter a problem like this, you're going to really just be using it on like one equation at a time. Like, okay, this is the thing I need to solve. This is the thing I need to approximate. You're probably going to try it 4 or 5 different ways and just making sure, how are you double checking every step along the way? The goal is to provide you more tools for kind of creating models, testing models, and then like I said before, trying to break your own model so that way you can be really confident when you have to defend your model. And so if that means for you, like I'm going to do this and then I'm going to go back and do this one separately and check them, like it doesn't matter to me how you do it. I want you to remember that your goal is to create a mathematical model that explains some phenomena, and then be the biggest like contrarian that you can think of. Try to break that model. Once you've done that, you'll have all the answers to the questions you're going to get. When people are like, how does that work in this limit? That doesn't match my intuition. No, actually, here, I can show you how that works. And so just remember that the goal is not for you to become efficient at doing these mathematical problems. The goal is for you to have the tools in your toolbox to address the research questions that come up.
Great, yeah. Thanks.
All right, it is 12:45. We will continue talking about singular perturbations next week. Have a good weekend, everyone.